Welcome back to ECE 442-542. This is the review session for exam number 3. Before we cover the topics, which I'm now displaying, and I guess you can pause this recording if you need to and write these down or just study those. As a reminder of what the process is, that really hasn't changed from exam to exam. It's just each time we have another exam, we add one more sheet of notes. You may not need that, but it's available to you. You have front and back. Now you have 6 pages of notes in addition to the transform table. Calculator, maybe even in addition to a protractor, you have a compass. If you want, that's allowed. Just don't stab your neighbor or yourself with that compass if you want to draw a nice circle. But you can do it by hand if you want. But are there any questions on the process for exam number 3? That should be fairly straightforward. Topics for exam number 3 are basically homeworks 5 and 6, and there may be other pieces. This is cumulative material. It's all starting to build, so you may have to know earlier stuff in order to do it. There is one more lecture that I didn't go over in class that's now posted on D2L that really covers the example that we sort of were looking at last time with 2 poles and a zero to the left of those 2 poles, and it walks through that kind of a root locus sketching and finding stability, etc. You might look at that to help with homework and this exam. You need to know how to sketch these different root loci. That's not here, but it is on the D2L website. You'll need to be able to go back and forth between transient performance specifications or suggestions and z-plane pole locations, or if you're given z-plane pole locations, can you get the transient performance that are consistent with those pole locations? Or given transient performance specs, can you collapse in on a particular region in the z-plane that would satisfy those performance specifications? All of those different ways of relating transient behavior with the z-plane pole locations you need to be comfortable with. You also need to be comfortable with the direct design method of Ragas Eenie, and that really, for starters, is very closely related to this transient performance. If you are told, I want these poles, or you need this closed loop system to satisfy certain behavior, transient behavior, that's going to influence your poles in this Ragas Eenie closed loop transfer function. Once you've found T sub C of Z, which has different restrictions possible, then you just turn the crank once you have T sub C of Z from our design formula to obtain the controller. The other control strategies that we've looked at are proportional and proportional integral design, and how do you sketch root loci for those kinds of controllers, P and PI. And that's the bottom section, is root locus sketching and properties. So let's look at this notion of transient performance and z-plane poles. You can look at it many different ways. One way is if you are given maybe the transient performance by a step response, can you extract the transfer function that produced that? That's system identification. Meaning maybe on the exam you might be given some response. That might be given to you. And now what you need to do is figure out how do you come up with the transfer function that corresponds to that particular, and here we're assuming it's a second order system. You now might identify the peak time. Maybe that's 1/4. Maybe the settling time, and you would have to eyeball that, but now you're saying you're within 1% of the final value. Maybe that's T sub S, and maybe that's 1. And from this plot, hopefully you could, so this is a plot of y of n. You now want to, once you're given this, you now want to find z delta and find, let's say, g of z. And maybe you're also told that this was actually going to a value of 3. So now with that information, you should be able to pull out the transfer function that corresponds to that transient behavior. Here you might have to be told what produced that. You might have to be told that a unit step produced this output response. So that now you know that the DC gain times the unit step is equal to 3. And you also might now say, oh, the time to peak, if that's 1/4, well, time to peak from maybe the analog setting that you've been playing with is this pi over omega sub d, but you know how omega sub d is related to the angle in the z-plane, this theta sub d. You know that theta sub d is omega sub d cap t, so that now you could say, well, this is pi over, solving this equation for omega sub d, you could say, oh, that's theta sub d over t. And now you can solve for theta sub d if you're given capital T, the sampling period. Because you know that pi t over theta sub d is 1/4, and theta sub d now is in radians. Now you know the angle of your poles. You can use this final value together with knowing that you had a unit step to determine the DC gain of your transfer function. The DC gain is now what? 3. You know what theta sub d is. What else can you use from this information? Pardon? Settling time. What's the settling time provide for you? The radius. And once you know the radius and theta sub d, you have your denominator, you have your z delta. You can figure out what your numerator constant is with the DC gain. You would evaluate that at z equal to 1 to determine what that unknown constant is in the numerator, and you could say, I'm going to assume a pure two-pole system. Or you could say, oh, I'm going to put 1, 0 at the origin and have my two poles determined by this transient behavior. Here you would use the settling time. You would say, oh, settling time is now n sub st. Again, you might have to be told what capital T is, but you can find R from that fundamental relationship, which is determined from your 1% settling time. You know capital T sub s is 1. If you now know what little or capital T is, you can solve for capital N sub s, and you can use the only unknown then in that boxed formula is R, and you can now solve for capital R. And Z delta, your poles of your transfer function, are R at an angle of theta sub D. So that now G, maybe I said, oh, you have a 0 at the origin. Now you might have some alpha Z over Z minus R e to the J theta sub D, Z minus R e to the minus J theta sub D. Or you could use R and theta sub D to get the real and imaginary parts in rectangular form, and then you have Z minus real part squared plus imaginary part squared in the denominator. Question? So now we typically have that Z in the numerator. We don't have a real, well, we have a real Z, but it's located at the origin. It might make the formulas a little less consistent if that Z is not at, I'm sorry, that if the numerator does not contain that Z at the origin. So you can, if nothing else is given to you, you can just assume that the numerator either contains that Z at the origin or it doesn't contain any Z in the numerator. And that's really, what does that Z do in the numerator? That just advances you one time step, really, relative to those two cases. So that Z is now an advance, and if it's not there, you sort of have two delays in your system. Relative to it there, you now have one delay. It's this pole zero excess idea where you have now 2 in the denominator and 1 in the numerator. Now you just have a 1 sample period delay net if you have the Z there. You have 2 if it's not there. And we're not going to probably worry too much about that. You'll be able, and at Z equal to 1, that doesn't mess up your DC gain calculation, having that Z at the origin, or the 0 at the origin. Yes? Yes, so now if you're doing the direct design by Ragas Eenie, you're going to have to simply realize that these formulas that we're using to specify the denominator are really only approximations. They're rules of thumb based on an ideal transfer function, and that ideal transfer function goes out the window a little bit if you have unstable zeros, because you have to preserve those in your, or even not at 0. That's correct. But your T sub C, a lot of times we will, well, I was going to say, no, we may have more than just deadbeat responses in T sub C. I was going to say that, but no, plan on having more than just deadbeat responses in your T sub C of Z. And we're not there yet, but let's keep going with this connection between transient and Z-plane poles. You might have to use those in creating a desired transfer function. By that, so let's say that the system ID piece was 1 for this transient performance in Z-plane. Now 2 is creating a desired transfer function. Suppose that somebody wants the following. They want a given percent overshoot, they want a given time to peak, and they want, maybe that's getting you confused with 1, 2, and 3, so let me say A, B, and C. Now maybe they want a given settling time. All of these together are put there to try to find a Z sub delta. What does the percent overshoot tell you? What information does that provide? Or if I say percent overshoot, what else are you pairing with percent overshoot? The squiggle, the zeta, the damping ratio. This is now zeta. What's time to peak providing? Or what are you connecting with that? That's now the angle. Settling time is now the radius, which in the Z-plane, you have the radius that should be centered on the axes. Maybe it's not. The time to peak now tells you an angle. And I saved red for the zeta because that's sort of this logarithmic spiral, which is sort of heart-shaped. And now I could give you all sorts of different ways of relating those. I might say you need a peak time less than a certain amount, where the certain amount is given by that green line. But now if I said less than, which side of that green line are you concerned about? Up or below? Or beyond or inside that angle? If I said a peak time less than, you now want your angle bigger, don't you? So now you're living above that green line. If I said less than, if I said a peak time more than, now you're inside that triangle. Inside that angle. What about percent overshoot? If I say the percent overshoot of something or less, are you inside the heart or outside the heart? Less than a certain percent overshoot. So now think of what, if you get lost or turned around, think of those logarithmic spirals relative to the unit circle and the real line. The unit circle, what kind of a response does the unit circle give you? If you had poles on the unit circle, what would if you had two complex poles on the unit circle, what would your system do if I walked up and kicked it? It would just keep going, wouldn't it? It wouldn't decay. It would just oscillate if you had poles on the unit circle. So what's that mean for zeta? Zeta is what on the unit circle? Zeta varies between 0 and 1, and zeta is your damping ratio. If you have no damping, what is zeta? 0. So that's on the unit circle. So less damping is on the unit circle. More damping is you're collapsing those hearts, those logarithmic spirals, down until you get to the real line. Then you don't have underdamped, you have these decaying exponentials. So now if you need a certain percent overshoot or less, which side of the heart are you going to be? Inside or outside? Inside. You want to be collapsing towards the real line. Is that clear? So now let's say I want a peak time less than something and a percent overshoot less than. Which intersecting region do I need to be worrying about locating my z deltas on? And I haven't even said anything about settling time, have I? But I want it to be, whoops. I want it to be peak time less than, so I'm there. I want it to be percent overshoot less than, so now I'm in that little, I don't know what shape that is, but I've shaded it. Is that, did I shade the correct shape? For percent overshoot less than, determined by that red heart or logarithmic spiral, and a peak overshoot, or a time to peak less than whatever that angle produced. Yes. No, not necessarily, because the question or comment was, are you also keeping it inside that blue circle? I didn't say anything about settling time, so I don't need to worry about the blue circle. But if I did have a settling time spec, then yes, it would have to be inside that blue circle. Now if I had all three and they weren't consistent, now what do you do? Let's say you have a percent overshoot spec, a peak time to peak spec, and a settling time spec, and they're not consistent. What are you going to do? You might need to know, how are they not consistent? They're just, one is not meeting all of the other two. Probably the quickest way to try to make them compatible is to shrink the radius if they're all sort of less than, versus trying to mess with zeta and the angle. It's probably quickest to just say, what happens if I collapse the radius? Then that's going to tighten up all of those others. But I might say something like, what if I now had a peak time more than something and a settling time less than something? Now I'm under the angle and inside the blue. And I didn't say anything about percent overshoot, but I could have imposed something there also. Is that clear how you're needing to play with that to try to identify your z deltas? The other way of looking at transient and z-plane is to determine the transient performance from the closed loop poles. And here you're just going to have to basically throw out zeros if they're in there. You're just going to say, I'm going to base all of this analysis on the closed loop poles and how I know they are related to one another. Here you would be given z sub delta, and you might be asked to find the percent overshoot, the time to peak, and the settling time. And you might actually be given time to peak and settling time and be asked to find the percent overshoot. Can you do that? You need to be able to, given 2, find the third. Is that clear? All of these are interrelated a lot of times by solving for omega sub nt in terms of the different variables that you do know and finding, let's say, zeta in terms of theta sub d and r. So if you're given settling time and peak time, you can now find the percent overshoot. You're basically looking at this radius and the angle and where they intersect, what zeta curve goes through that intersecting point. That's really what you're asking or answering. So you could draw this if you were really good at sketching, if you figured out what the zeta values were. Is that making any sense? That's this Z delta transient spec connection. What about another topic? That's Ragas Eenie. And in Ragas Eenie, the big thing is really creating T sub C. But you have to create that based on different restrictions. Restriction 1 is causality. That basically says your controller has to be causal. But what's the causality constraint mean in practice relative to T sub C of Z? It has to have the same or larger pole zero excess as your original system. If your original system has a pole zero excess of 2, you have to have at least a pole zero excess of 2 or more in T sub C of Z. That's the causality restriction. And it really doesn't matter what order these are, but I think just for talking about this, I've tried to be consistent. The second restriction is if you have unstable zeros in your system. You don't want your controller doing what? You don't want your controller canceling those unstable zeros, and to prevent that, you have to put those unstable zeros in T sub C of Z. That's restriction 2. That's why those are forced into T sub C of Z. Restriction 3, if you have unstable poles in G of Z, you definitely don't want your controller putting zeros to cancel those. And to offset that possibility, that's what restriction 3 solves. And now you need the zeros of 1 minus T sub C of Z to be at the same location as those unstable poles of G of Z. And then you get the cancellation in your design formula, and your C of Z doesn't end up with zeros where those poles are. Finally, you have restriction 4, which is dealing with steady state accuracy, which might be the DC gain of T sub C of Z. It might be you need a certain steady state accuracy due to more than just a constant. Maybe you need a certain error due to a ramp signal. That's restriction 4. Once you've built this, that's the hard part. Building T sub C of Z. The straightforward part is plugging those into this design formula, which is really inverting the plant and then scaling that or adjusting that to where the end result of this unity output feedback configuration with this cascade combination of the controller and the plant giving you a closed loop transfer function of T sub C of Z. And on the exam, I may not have you find C of Z. That's kind of a straightforward process. The more important part is finding capital T sub C of Z. So unless I say find the controller, you probably aren't going to be asked to find the controller. The hard part is finding T sub C of Z to satisfy these four restrictions and maybe to meet some transient performance spec. Maybe I say have a % overshoot of this and a settling time of this in your closed loop. That's giving you your denominator. And then what happens if you have two unstable zeros and you just were told design specs which give you two poles in T sub C of Z, and you know that the original system has a pole zero excess of 2. I have too many 2's. 2's are wild. How about we have a pole zero excess of 1? Pole zero excess of 1, two unstable zeros in your original system, and you have design specifications in T sub C of Z that are specifying a second order denominator polynomial. Do you have to do anything special to meet any of these restrictions? Can we keep track of all that? And on the exam, write things down. Don't try to keep everything in your head. Just write that stuff down. Oh, two unstable zeros. I need to worry about restriction 2. Pole zero excess of 1. Where does that come into play? That's restriction 1, isn't it? You need to make sure that T sub C has a pole zero excess of at least 1. It could have more. But how are you going to do that? You have two unstable zeros and two poles. What's your pole zero excess right now? 0. So what do? You need to add some z's into the denominator. Z's not to fall asleep, but z's to make your pole zero excess better. And the best place to put those might be right at the origin. Just add 1 right at the origin. Now your denominator is third order. You have the correct pole zero excess. Unless you have some restriction 4 that requires you to put another 0 factor in play to meet steady state error specs. Then you add another one at the origin, another pole at the origin. If you've now introduced a third 0 factor. 2 because you had two unstable zeros. Is that clear how that might work? Let's look at an example. Suppose G of Z is now Z minus 1/2 Z minus 1. And we won't go too crazy since this is a review session, but suppose our goal is that we want a closed loop system that has a deadbeat response. What might we you just woke up and you go, gosh, what might you try just in a stupor? We want a deadbeat response, so where do we want our poles? At the origin. How many poles do we need? In T sub C of Z. What if I simply said, can we use T sub C of Z equaling 1 over Z? Does that meet restriction? So what are our constraints or restrictions? And now we would just say, okay, let's see if our constraints or restrictions are okay. What about restriction 1, our causality? Is the pole zero excess okay in T sub C versus G? What's the pole zero excess in G? 1. What's the pole zero excess in T sub C? 1. Cha-ching. Right? What about restriction 2? Do we have any unstable zeros in G of Z? No, so we don't need to worry about restriction 2. So R2 not applicable or does not apply. What about R3? What's R3 dealing with? Unstable poles. Do we have any unstable poles? Yeah, we have that crazy one right on the boundary, so that one you really kind of need to worry about. And what do we need to do for this one? R3 says that we want 1 minus T sub C of Z. Where do we evaluate T sub C of Z? At that location, right, which is Z equal 1. And we want that to be 0, don't we? We need this quantity, 1 minus T sub C of Z, to be 0 at that unstable pole. And maybe by luck, it does, doesn't it? If T sub C of Z is 1 over Z, we're looking there, we have 1 minus 1 over 1, and that is 0. 3 is satisfied, restriction 3, just with that 1 over Z. What about constraint R4? Did we say anything about steady state accuracy? No. So R4 really isn't in play, is it? We don't have to worry about steady state accuracy, but what can you say about steady state accuracy based on G of Z? We actually had an open loop pole at Z equal 1. And what does that do for us? Can we say anything about the error? If our closed loop system is stable, is our closed loop system stable? T sub C of Z, we would be looking at the denominator, and the roots of that are inside the unit circle. They're at the origin, so it's stable. What's the steady state error due to a constant input when we have a pole at z=1? That's like our PI controller, isn't it? It forces a pole at 1. There will be zero error to a constant input in this system. So if we wanted to find that controller, C of z, that would be 1 over g of z times t sub c over 1 minus t sub c. And a lot of times it's maybe easier to sort of play with some of this on the side. This is now 1 over z, and this is z minus 1 over z. We have 1 over z minus 1 is t sub c over 1 minus t sub c, and c of z is now 1 over, and what was g of z? That was z minus 1 half, z minus 1, all times 1 over z minus 1. And our controller then is z minus 1 half. To find or to produce a closed loop transfer function t sub c of z that's what? A delay, 1 over z. So that now if we had to sketch the block diagram, there's our controller, our plant. Look what that controller's doing. What's it doing? It's doing this and that. Are those okay to do? It's canceling a 0. It's canceling a pole. Are those pole and 0 cancellations okay? Yes, because they're inside the unit circle. So now our block diagram simplifies actually in this controlled configuration. And from our cheer, we know that t sub c of z is g over 1 plus g. So that's what we needed. If we now said, if I said, give me the difference equation for that controller in the system, now you could say, oh, C of z, which was U of z over E of z, meaning here is our U of z and here is our E of z. I want to know what's the difference equation that relates the air to the input to our plant. This is now equal to whatever it was, which was z over z minus 1 half. And sometimes it's a little bit cleaner maybe to put that in terms of z to the minus 1s. If we wanted to, we could now multiply that by, what do we want to do? We could do all sorts of things. We could say this is Why don't I multiply that by z to the minus 1? So that I now have 1 over 1 minus 1/2 z to the minus 1, so that I have 1 minus 1/2 z to the minus 1 u of z is equal to e of z. Did I do that right? So that now in the time domain I have u of n is equal to 1/2 u of n minus 1 plus e of n. So that the input going into my plant takes the present air and adds to that 1/2 of the input to the plant one time step in the past. And that's an easy computer program to write to produce this controlled system that now behaves like a delay. And it sure didn't start out as a system that was a delay. It had a 0 and a pole at the origin and a pole at 1. Questions on Ragas Eenie? Getting hungry, saying Ragas Eenie. I think somebody had some Ragas Eenie before class. Maybe not. Oh, you can't smell on the tape, can you, on the recording? You miss that sense. You guys may design that in your lifetime, right? To where now you really have this immersive behavior. Now you get this lecture and you can smell it. But your sense of smell is very memory specific. Maybe that's what we need to do. Maybe you would really learn this stuff if every time we talked about Ragas Eenie, we had this really pleasant smell. And then every time you'd walk through the union, you'd go, Ragas Eenie design, what? And you would just start designing these controllers. You might walk into your mom's kitchen and, Mom, your meal reminds me of a Ragas Eenie controller design. What? No, Mom, that's a good thing. All right, where were we? I don't know. Let's look at some, you need to be comfortable with sketching root locus patterns. And what I would suggest is on the exam, quickly draw these sketches. And if it's not right, just put an X through it. Don't try to erase. Don't spend time erasing. Just restart and draw another one. What if I sketched this pole 0 pattern? And maybe you're told that. Is there a range of K for stability? If this is now the plant and you know you're in a negative unity output feedback configuration, the root locus is almost trivial, isn't it? It now looks like this. And now the lower limit for stability is there and the upper limit is there. You find those gains and you have your range of stability. What about a pole 0 pattern like that? How many pieces of the French bread have been identified? 3. How many of those are on the root locus? 1. And which piece is it? Infinite, finite, or infinite? Finite. Bummer, we don't get an infinite piece of French bread. I'm hungry. But we have that, don't we? And now, depending on where the unit circle is, you have to determine your values of gain k based on that almost trivial root locus. And that's all based on Rule 1 and Rule 2, isn't it? And if you have basically sort of the counterpart of that, it's similar, except now, what? You're moving in the opposite direction, from left to right instead of right to left. What about that? What's the pattern now for the root locus? What's the pole? Is there a part of the root locus on the real axis? Is it finite or infinite? Is it between the poles? How many branches of the root locus are there? How many poles or how many zeros are there at infinity? 2. What are the asymptotes? This is Rule 4, but your root locus is going where? As you crank up the gain k, where are these branches of the root locus going? Or where are they headed? To plus and minus infinity? Real infinity? I. Now they're going, I. Now they're going up and down, aren't they? Plus and minus 90. And where do these two meet? In this, because you have two isolated poles, no other poles and zeros, they are going to meet exactly halfway between. You don't even have to calculate the relative max. You know it's going right between. And they are not bending. They are going straight up and down at plus and minus 90 degrees. And depending on where the unit circle is, if that rightmost x is inside the unit circle, do you have to worry about stability? If I've given you the location of those poles, could you determine the maximum value of gain for stability? If I've now told you, I'm going to make my life miserable now, but let's say that this is 0.8 and this is 0.2. Can you find the gain k? So now you know that g of z, I'm going to make it a little bit easier. Let's say that the numerator is 1, so that I now have z minus 0.2 that's my transfer function that I'm going to put into a negative unity output configuration. Can you find the gain k, the upper bound on k for stability? What's the lower bound? 0. You have an open loop stable system. I'm just going to draw a fourth of a circle, and then you won't know that my other 3/4 is really pretty bad. But I have a circle. Where that intersects that circle is the maximum you can crank up the gain to remain stable. Can you identify that point? It's really not that hard because you know the Pythagorean theorem. You know the radius of the unit circle is 1. You know the real part of that complex pole. If I call this the triangle point, Z delta is now what? Those two poles are separated by a distance of 0.6. Half of that is 0.3. Keep me honest. 0.3 plus 0.2 is 0.5. So the real part we know is at 0.5. Plus JB. J being the square root of -1. But we know that the real part squared plus the imaginary part squared, square rooted, is equal to 1 because it's on the unit circle. The only unknown in that is B. You can solve for B. Is that clear? Once you know B, now from the magnitude condition, you know that K is Z minus 0.2, Z minus 0.8. You can evaluate that at 0.5 plus JB. And that's your gain, the maximum gain K for stability. And the magnitude of that complex number on the left should equal the magnitude of the one on the right because they're equal distance. Those are basically just hypotenuses from those poles to that triangle location intersecting the unit circle as a check on your work. Is that clear? How you could find that? What else do we want to see for patterns? Suppose we had that. I don't know why my notes tell me otherwise, so let me push this over here. Let's say that this is, oh no, I was thinking wrong. What am I doing? I saw 2 and was thinking 2, but let's say this is now what we have. What can you tell me about the root locus here? Makes a circle, doesn't it? What you don't know without calculating it is where the radius of that circle. But you do know this real axis piece. You have 2 branches of your root locus on each real line segment that belongs to the root locus. You can compute the relative maximum between 1/2 and 1, and let's just say it's right there. Now this defines the radius, and that radius is the same. Oh, now I've set myself up. But you get the idea. That's the same, and so this distance is R. You don't really have to find the re-entry point directly. You can find it indirectly by computing or finding the breakaway. The breakaway occurs between the 2 poles. They get so high in gain, and then they're right on top of each other, and they can't go through each other. They have to leave the real line. Then they leave the real line, and they come back in the same distance away from that 0. And depending on where that 0 is, that's going to influence stability behavior. But now you have this going there, and then one branch goes right and one goes left. Is that clear? What's another pattern? See how you could just sit at home and entertain yourself with all these patterns? And we're just doing 2 poles and 1 0. which way is the root locus branch going from that rightmost pole? Right or left? Is it clear that the pole on the right is moving to the left to approach that finite zero? What's the pole zero excess? 1. How many poles or how many zeros at infinity? 1, and that 0 is over here. And depending on where all of those are located, it's going, if this, let's say, is 1, and let's say this is -1, what do you hope happens to this if you wanted to have a stable design with a gain-controlled system, and these were your poles and zeros? What would you hope happens in this configuration? What do you need to happen on the right for stability? You need to make that pole on the right get into the unit circle. So you need to crank up the gain to get you to 1, but what do you hope not happens on the left? You hope that pole on the left doesn't zip out of the unit circle before the one on the right gets in. Is that clear? What you're hoping is that the gain to get you to that unit circle here maybe only get you there, and then maybe this guy gets there and this one gets there. Is that clear? That's what you're hoping for. What you're not hoping for is the triangle on the left is to the left of -1 when the triangle on the right gets to 1. If that's the case, then is this system stabilizable with a gain? No, you can't stabilize this system with a pure gain controller. Is that clear? How you could determine that from just the pole zeros and where they're located? Oh, let's get a little bit more interesting. Suppose that we now have a pole there, a pole here, and a pole here, where this is now at 1, this is at, so you'll need to draw these better than I am. Now I'm getting ahead of the game, maybe, versus what we've talked about so far. But, you know, we're playing now. What's the pole zero excess? 3. Haven't seen one of these, have we? How many zeros at infinity do we have? 3. So where are they located? They have to be located such that if those 3 poles went to one of those root locus locations, their angles would sum up to -180. Which means what? Well, first off, let's just find the real axis line segments. Dr. Tharp, you made it too hard too quick. Okay, let's just start with what we know. What do we know? We can find the real axis pieces that are on the root locus, can't we? Before you just throw in the towel. You don't have to play that much along, but that's okay. So somebody did throw in the towel, but not on the exam. This is still practice, right? So we're still in spring practice. This, what color am I? Let's do this. So here's a piece and here's a piece. Is that true? Do we have any breakaway points? How many root locus branches do we have? 3. How many root locus branches are between 1/2 and 1? 1, 2, or 3? 2. We have 2 poles and they're going towards each other. Now, which way is this pole going on the far left? He's probably zipping off to minus infinity. Okay, Dr. Tharp, that's all you've taught me so far. Well, let me teach you a little bit more. Now, if we went a long way from those 3 poles, and we looked back at those 3 poles, what would we see? How many poles would we see? So we go way away. I know my eyes are pretty bad, but I can still see what? How many poles? 3 poles. So they're all 3 going to contribute to where I'm standing. Is that clear? It looks like 3 poles clustered maybe in one place, and we're going to call that one place our centroid. The centroid of those 3 poles. So if I have 3 poles at the same location, where must I be standing at what angle away from that centroid in order for those 3 angles? They're going to all 3 give me the same angle, but those 3 angles have to sum up to minus 180 to be on the root locus. So it's going to be at 60 degrees, isn't it? I have a 60, a 60, and a 60. I'm going to subtract all 3 of those, and I'm going to be at minus 180. What if I traveled way down the minus 180 and I looked back? I'm going to have 3 poles at the same centroid. They're each going to give 180, so that's going to be on the root locus. So I'm saying or suggesting that I'm going to have something (60 degrees). I have something at 180, so this angle is how much? And I really need to be splitting 360 degrees into 3 equal pieces. And those 3 equal pieces are going to be separated by 120 degrees, aren't they? So I now know that that other piece is going to be at minus 60, which is 120 from that other asymptote. These dashed lines are my asymptotes. The asymptotes are where the branches of the root locus are going to approach as the gain k gets really big. And where those asymptotes are centered is the centroid. We'll talk about this at more depth after the exam, but do you get the idea what's going on? How many zeros at infinity did you have? So what you will see is that you will have 180 divided by the pole 0 excess, which gives you this fundamental angle, and then you can use that to figure out where all the others are. Suppose you had 4 poles, no zeros. What's the pole 0 excess? 4. Now your fundamental angle is 180 divided by 4. 180 divided by 2 is 90. Divide that 90 by 2, 45. So now you have 45, and things are going to be separated by 90. So now you have 45, 135, something and something, minus 45 and minus 135. How's that? Is that clear, sort of? Do you get the idea? We'll talk about those centroids, and But what's going to happen is these two are going to come together, and this one's going to go up here, this one's going to go down there, and this one's going to march off to minus infinity. Is this system ever stable based on this picture, root locus? And these root locus diagrams look pretty clean. They don't go real weird with how they are sketched. These are fairly smooth curves. Why? Because their angles are minus 180 all the time. But is this system ever stable? How many think yes? Give me a hand. No, not that kind of a hand. A raised hand. So yes, it is stable, isn't it, initially? What would you be checking for the maximum value of gain K? You would be looking to see where that curved one is going through the unit circle and where that one at minus 1/2 is going through minus 1, and you would be comparing those two gains. And if the gain to get you outside the unit circle from these branches at 1/2 and 1 was bigger than the gain to get you to minus 1, then the minus 1 would be the maximum for stability, gain-wise. Is that clear? Yes. You might have third-order polynomials, but you might have 3 poles, you might have 4 poles, but you might have counteracting zeros. So you probably won't have these shapes to worry about. But I think it's good for you to start to see something. For example, I didn't hear that last question. Somehow my hearing has just become completely faulty, but I don't even know what was asked. So let's look at this next question. Do I have it enough here? 1, 2, 3, 4, 5. When I say probably won't be, don't worry about it on the exam. Okay, I think that was the question. But now you're given this configuration. Ouch. What's the pole zero excess? It's getting late, isn't it? How many poles do we have? How many root locus branches do we have? 4. What's the pole zero excess? 2. So how many zeros at infinity do we have? 2. And where do we know those are going? When we have 2 zeros at infinity, where are they going? Up and down, aren't they? So we know that we're going to be approaching asymptotes, but now those may not be straight up and down. They may be curving to those asymptotes. Which line segments belong to the root locus? Here? Oh, I shouldn't hold my pen down so long. Stop. Okay, so now I'm going to try not to touch it. Oh, and you can't see, can you, if I don't touch it? How about here? Is this on the real root locus? What about here? The next one over? The one to the left of the first zero on the right. The next one between the zero on the left and the pole on the right. The one between the leftmost pole and the right and the leftmost zero. You laugh. Something to that effect? Is that okay? Now what's happening? Do you have a breakaway anywhere? Where is that breakaway? I didn't resketch my horizontal line the same, did I? But you get the idea. And these now are going to maybe do this, depending on where you would calculate the centroid. You know the asymptotes are at plus and minus 90. This guy's going there, this guy's going there. Is that clear? And depending on where the unit circle is relative to those, depends on whether you have a stable system or not. Yes? I'm sorry? I'm not quite understanding the question. So now the pole can either go left or right towards a zero. It doesn't always have to be going from right to left. These both are going left to right, but we have one pole on the far right going right to left. So how things move all are influenced by the relative locations of the poles and zeros. You can't just generalize and say this is always going to be the case. Is that clear? I don't want to scare you, but I do want to get you thinking about these different patterns and how you already know a lot about these root loci. So use that to your advantage on the exam on Wednesday. Again, quickly sketch. If you think it's wrong, cross it out and do it again. Ask for paper if you need more paper. Any other questions before we quit? You've been very patient. Yes? Yes. 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 So the question was, what if this particular pattern was such that, I don't know that I want to do this, but I will, is something like that. Then K can be between 0 and infinity, and you're still stable. Does that answer your question? Yes. So really when K is equal to 0, what I would sort of suggest that you do to sort of get a feel for what's going on, I don't know why I'm scrolling back because I don't think it's going to help me any, but I'll just do this a few times and then maybe it'll all, no. Let's say that now K is 0. You wouldn't have any transmission through that system, would you? So at K equals 0, sort of think that you've disconnected the feedback and you don't have your controller is 1 and you now just have an open loop system. That's sort of the concept or the idea with K equal to 0. So now replace this leftmost block with 1, disconnect the feedback. That's now saying K is equal to 0. We don't have any feedback, and you just have an open loop system. Your poles are in the open loop location. But as soon as you bump that K up a little bit, you've introduced feedback, you've now adjusted the K, and you're back in your warm and fuzzy environment. If that doesn't help, don't worry too much about that explanation at this point. Okay? Yes. How can you calculate the radius? So to calculate the radius, if you have 2 poles on the right and a 0 on the left, You calculate the radius by first computing the breakaway point. You need to locate where the two branches of your root locus. The question was, what if we have, I think, this scenario? You now need to compute, where am I breaking away? Once you've computed this location, you can use that to determine what this radius is. That radius now is determined. Pardon? So now to calculate the breakaway location, that's the relative maximum of K determined by your K formula. So you'd have to know where your poles and zeros are. But if this was, let's say, at B, and this was at A, and let's say this was at minus C, then you would have a K that's Z minus A, Z minus B over Z plus C, assuming there was no gain in the system, variable in the system. And you could iterate that between Z equal A and Z equal B, I mean number crunch, and find your K value, and where it reaches a relative maximum, that's where you're breaking away. You could numerically do that for a few values of Z between A and B. And that's how you could compute your breakaway. You could do it by differentiating that expression. I would remove all the absolute value signs, differentiate just like calculus, and find where your relative max is. And that gives you your Z location. Then you can compute K at that Z value. And once you know that breakaway point, there's your radius based on wherever that zero was. So we'll stop there. If you have other questions, we'll do those offline. We'll let the others go home. Some of you will enjoy some Ragas Eenie this evening, and we'll see you on Wednesday.